Hi student, welcome to chemistry class with Emerald. In this class today, we are going to be looking at the definition of acid and base based on the Arrhenius theory. This video is brought to you by Agota Virtual Learning. And in this class today, we are going to be looking at the definition of Arrhenius acid and take some few points under this definition. We're also going to look at the definition of Arrhenius base and also some few points under them. We are going to look at the achievement of Arrhenius theory on acid and base. We look at the limitation. We are going to look at the effects of acid and base on indicators such as litmus, methyl orange, phenolphthalein, and so on. We are also going to look at reaction of acid and base on zinc, iron, and the triazocarbonate 4, and of course do some activity. I hope you are going to enjoy the class today. So let's go. Let's define Arrhenius acid. Arrhenius acid is a substance that produces hydrogen ion in aqueous solution. Or we can say a substance that contains hydrogen and ionizes to produce hydrogen ion as the only positive ion in aqueous solution. An example is what you have seen here. HCl ionizes and produce H plus and Cl minus. Emphasis on the H plus. The same thing with HNO3 ionizing to give H plus and NO3 minus. Note that Arrhenius acid can be monopotic or monobasic, can be dipotic or dibasic, it can be tripotic or tribasic, depending on the basicity of the acid. And other example of the acids include a dipotic acid, which is H2SO4. It will ionize to produce 2H plus and SO4 2 minus, and of course H3PO4 that will ionize to give 3H plus and PO4 3 minus respectively. But for Arrhenius, it defines its acid as substance that produce H plus in aqueous solution. Now let's take some few points here. Under Arrhenius acid, because they dissolve in water, water is the solvent for dissolving the acid now. So since water is solvent, their water solutions are known as aqueous solution. And acid in aqueous solution are known as aqueous acid. Acid in aqueous solution are known as aqueous acid. And then all aqueous acid are electrolytes. They can be used in electrolysis. Because of this ionization, therefore, according to Arrhenius, acid can be classified as strong and weak. Strong acid ionize completely in aqueous solution, while weak acid ionize partially. Example of strong acid are HCl, H2SO4, HNO3. An example of a weak acid is ethanoic or acetic acid. A key point to also take note of is that the key point of Arrhenius definition is that acid increased when there is increase in concentration of hydrogen ion in aqueous solution. When an Arrhenius acid dissolves in water, it releases H plus, which combine with H2O to produce hydronium or hydroxyonium. That's a very key point. When you dissolve an acid in water, the H plus goes into the solution and combine with the water to give H3O plus. So in Arrhenius definition, we have hydronium ion being present. Now the The process of dissolving in water to produce hydrogen ion increase the overall hydrogen ion concentration, making the solution acidic. That means the pH will be less. Don't forget in one of the in last video we talked about, as the hydrogen ion concentration increases, the pH reduces, making the solution more acidic. So the more the H plus concentration, the less the pH and the more acidic the solution becomes. Another key point of Arrhenius' definition of acid is that it is specifically for acids and bases in water. That means water is predominantly the solvent, meaning that the increase in H plus or OH minus concentration must occur in aqueous environment. So for Arrhenius, it must occur in aqueous environment. That means these ions, H plus ions, they don't exist as free protons in solution. Instead, they must combine with water molecules to produce H3O plus. This is crucial in understanding how acid behaves in water. So the second key point is that it must occur in aqueous environment. Now let's look at Arrhenius base, a substance that contains hydroxide ion in aqueous solution. That's OH minus. An example is sodium hydroxide that produces Na plus OH minus. Another one is potassium hydroxide, K plus OH minus. Now, let's take a few points under this. When a base dissolves in water, it dissociates. That means it breaks apart into constituents. For example, Na plus NaOH dissolve in water to produce Na plus and OH minus. The presence of OH minus is the defining characteristic of an Arrhenius base. It must produce, or it must have OH minus, like that of acid that must have H plus. Many bases are ionic compounds. Many bases are ionic compound. They have hydroxide ion as their anion, which is released when the base is dissolved in water. Please take note of this. Arrhenius base are usually ionic compounds that has OH minus as their anion, and when they are dissolved in water, they produce that OH as the only negative ion in that solution. So when they combine with acid, salt and water are produced. That reaction is called neutralization. And the heat generated from this reaction is called the heat of neutralization. Let's look at the key points or the key achievements of the Arrhenius theory of acid and base. Number one, with Arrhenius theory, we're able to identify and differentiate electrolytes, and of course, between strong electrolyte and not weak electrolyte. We are able to identify acid and base as electrolyte. All acids and base are electrolyte. His theory also helps us to differentiate between a strong and a weak electrolyte. Permit me to also say that one of the achievements of Arrhenius acid and base again is that it's able to provide foundational knowledge of acid and base in aqueous solution. This is the primary achievement of Arrhenius theory. His work basically gave us a foundational knowledge of acid and base in aqueous solution. He was able to also explain neutralization reaction and heat of neutralization. The theory also helps us to establish the concept of ionization in aqueous solution and the role of ions in chemical reaction. His work also provides foundation for further theories to be postulated. Foundation for other theories to be postulated. Now, may I say this on Arrhenius base that under Arrhenius base we could have bases that are soluble in water, which are called the alkalis. An example is sodium hydroxide, potassium hydroxide, and calcium hydroxide, while others are insoluble in water. Okay, so let's look at the limitation of Arrhenius theory. The limitation of Arrhenius theory. Number one, it is limited to aqueous solution. In chemistry, we have two major types of solution. We have aqueous solution and chemical solution. An aqueous solution is a solution that has water as its solvent, while chemical solution is a solution that has any other solvent as its main solvent. So Arrhenius limits his work or his definition to aqueous solution. That means that water must be the solvent of course, we had various solvents which we are going to be exploring. Arrhenius define acid and base based on their behavior in water, specifically production of H plus and OH minus. However, this definition does not apply to reactions in non-aqueous solvents or reaction. So this is the primary limitation of the theory. Now, another limitation is that it does not account for basic property of some certain compounds. It does not account for basic properties of some certain compound. For example, ammonia. Ammonia is a base, and because ammonia will dissolve in water to produce OH minus, and the definition of a base is that it's a substance that produces OH minus in aqueous solution, and this is an example of it. So it was not Arrhenius theory was not able to account for the basic properties of some of these substances, ammonia, the metal oxide, and certain salts, e.g., sodium triisocarbonate 4. They do not contain OH minus but still exhibit basic properties in aqueous solution. So it was not able to account for that. That's another limitation. Another limitation is that it was unable to explain neutralization reaction without ions. Although he explained neutralization and heat of neutralization, but he was not able to explain it deeply without ions. What do we mean by that? His theory focused on ions in aqueous solution, making it difficult to explain a neutralization where the resulting salt may not be explicitly ionic. And a typical example is when you have an organic acid reacting with a base to form a metal ethanoate and water. So, and as a typical example, when you have a benzoic acid reacting with sodium hydroxide to produce sodium benzoate and water. Sodium benzoate is not explicitly ionic. How do we know that? In sodium benzoate, for instance, the benzoate ion is not held together by an ionic bond. Instead, they are bonded by a covalent bond. So we cannot say it is specifically ionic. So it is not specifically ionic. So cases like this were not explained by Arrhenius. That's the third limitation. Another limitation is that is limited to non-hydrogenated acid and base. Limited applicability to non-hydrogenated acid and base. The theory is primarily applicable to acid and base with formulas like HA and BOH. What do we mean by that? For acid, it must have H. For base, it must have OH. That is what Arrhenius theory is limited to. However, we understood that some substances do not contain HA and OH and are still showing acidic and basic property. An example of that is CO2. CO2 would dissolve in water to produce an acid, or will dissolve in water to produce H plus, because it produce H2CO3, which will further ionize to produce H plus and CO3 2 minus. So in and then the other case SO2, another case AlCl3, which has acidic properties as well. So because they do not have H plus does not make them not acidic in nature. And then another instance is this CO2 again that will combine seamlessly with sodium hydroxide to produce a salt and water, which is also a basic property of an acid. So his work is limited to acid having HA and base having BOH formulas. Another limitation is that it doesn't explain acid-base behavior in non-aqueous solvent. The theory does not account for the acid or basic behavior of a substance in non-aqueous solvent like benzene or other organic solvent. Some certain acid and base have certain behavior in non-aqueous solvent, e.g., glacial acetic acid, in which the strength of the base will increase. When glacial acetic acid is in a non-aqueous solvent, the strength of the base will increase, while when the basic solvent is in the acid, the strength of the acid will increase. So these are limitations of the Arrhenius theory. Now let's look at the effect of acid and base on indicators. The effect of acid and base on indicators. Acid and base can change the color of acid-base indicators. Examples of these indicators are the litmus paper. For litmus paper, a common indicator, it turns red in acidic medium and turns blue in basic medium. Other indicators include methyl orange and phenolphthalein, which also exhibit distinct color change in acidic and basic environment. Note that this color change in litmus are due to the reaction between indicator and the hydrogen ion or hydroxide ion present in the solution. Let's look at litmus. In acid, for acid turns blue litmus paper red in acidic solution because it reacts with the H plus from the acid. A base in basis for base turns red litmus paper blue in basic solution due to the reaction of the OH minus from the base. And in neutral solution do not affect the color of a litmus paper. Neutral solution does not affect the color of a litmus paper. For other indicators, for methyl orange in acidic medium, it will turn methyl orange red. For basic medium, it will turn methyl orange yellow. For phenolphthalein, it will remain colorless in acidic solution, but it will turn pink or red in basic solution. For universal indicator, as far as acid is concerned, it changes the color of a universal indicator from green to red, and base will change the color of a universal indicator from green to purple. Let's look at the mechanism of acid and base on indicators. Acid-base indicators are weak acid or base. They are undissociated and dissociated form have different colors. That means before they react with acid, that's the undissociated form, and then when they react with acid, each of these forms that they take have different color. When an acid or a base is added to a solution containing that indicator, the equilibrium between two forms of that indicator will shift, causing a color change. So in acidic medium, the equilibrium position shift to favor the undissociated form of the indicator, while in basic solution, it shift to favor the dissociated form. So let's look at the reaction of acid and base with zinc. Zinc is a moderately reactive metal, and it can react with both acid and base to form hydrogen gas and a salt. Emphasis on hydrogen gas and a salt. So when zinc reacts with both acid and base, it forms hydrogen gas and a salt. Let's look at that reaction. For instance, you can have zinc reacting with dilute mineral acid like HCl to produce zinc chloride and hydrogen gas. With a base, if zinc reacts with sodium hydroxide and water, for instance, it produces sodium zincate and hydrogen gas as well. And this is the reaction with HCl, and now you can also react with H2SO4 as well in this case. Okay, so let's take a key point from reaction of acid and base with zinc. Number one is that zinc is an active metal, like I've said, and readily reacts with both acid and base. The reaction with acid is exothermic. That means heat is released. Take note of that. The hydrogen gas produced in that reaction, in both reactions, is flammable and can be detected with a burning splint. It can be detected with a burning splint. Zinc is also able to react with certain non-metals. Let's look at reaction of acid and base with iron. Iron will react with both acid and base, leading to different outcome. For zinc, we know it produces hydrogen gas and a salt, but for iron, it's different. Of course, again, iron is also a moderately reactive metal. Acid will dissolve iron, producing hydrogen gas and iron 2 or iron 3, depending on the acid and the oxygen present. For instance, when an acid reacts with iron, it will produce hydrogen gas and, for instance, iron 2 salt. And then if there is excess presence of oxygen gas, the iron 2 can be easily oxidized to iron 3. Base can also react with iron, but the reaction is less common, and often it also leads to formation of hydrogen and a ion containing compound that is complex. Let's look at that reaction. For the acid reaction, it will react with H2SO4 and so on to produce iron sulfate and hydrogen. Of course, note that for the iron sulfate here, it is iron 2 sulfate. So in the presence of excess oxygen or air, the iron 2 can be changed to iron 3. So it becomes from green to brown. In basic solution, bases generally do not react with iron to produce hydrogen gas. Take note of that. However, some bases like strong alkalis can react with iron under specific condition in the presence of water to produce hydrogen gas and complex ion compound. So let's look at this reaction, like when sodium hydroxide reacts with iron in the presence of water to form sodium ion compound, as we have seen here. Key points again. The reaction of iron with acid is more common and generally involve formation of hydrogen gas and iron salt. The reaction of iron with base is less common and depends on specific conditions. Moisture, pH, and presence of other ions can affect the rate and extent of these reactions. Now let's look at reaction of acid with triazocarbonate 4. Triazocarbonate 4 salt like Na2CO3 react with acid to produce CO2, water, and a salt of the original acid. An example is Na2CO3 reacting with HCl to produce NaHCO3, which further react with NaCl and produces, which further react with it produces NaHCO3, that's sodium hydrogen triazocarbonate 4 and NaCl. And then the sodium hydrogen triazocarbonate 4 react with excess acid to produce sodium chloride, CO2, and H2O. So basically, when triazocarbonate 4 reacts with acid, they produce the salt, CO2, and water. Please take note of that. Those reactions are very good applications in the laboratory and industry, especially acid-base titration and neutralizing acidic solution. Let's take off on key points again. Triazocarbonate 4 salt reacts with acid to produce carbon dioxide, water, and a salt, like we have mentioned. Another one is that triazocarbonate 4 salt are generally not reactive with a base. Take note of that. Except in a very specific area or with concentrated alkali solution. They are ever capable of forming complexes with certain metal ions. They won't react with a base because they themselves are basic in nature, except for special conditions, as we have said earlier. And the third point is that triazocarbonate 4 salt dissolve in water so they can undergo hydrolysis, meaning that they can react with water molecule. When they react with water molecule, it can lead to a slight increase in pH and formation of bicarbonate ions and hydroxide ions, respectively. Okay, so let's look at key activities. The first question, the color of methyl orange in alkaline medium. The answer is yellow, like you have seen in that in our previous videos, in the other slides rather. Another question is the color of litmus in a neutral medium. It is purple. The answer is A. The third one, which of the following compounds react with sodium hydroxide to form a salt? The answer there is A, which is propanoic acid. Like we have said, organic acid will still react with a base to form alkanoids, metal alkanoids. And this is also known as neutralization reaction. It was explained in previous slides. And then the last one here is when you have H plus and OH minus to produce H2O, what type of reaction is that? It is neutralization. The H plus is from acid, the OH minus is from base to form water. The reaction is neutralization. So far we have been able to look at the Arrhenius theory of acid and base and taking some few notes on them. We've looked at the achievement of that theory and we've looked at the limitations of that theory. We've been able to look at the action of acid and base on litmus, action of acid and base on indicators, rather on zinc, on iron and on calcium carbonate for salts. This is the end of the lesson for today. Continue to learn chemistry. Bye for now.